Hi everyone. This lecture is going to have two learning goals. The first is to understand the key types of multivariate statistics, and the second is to understand how to interpret multivariate statistics. Just revisiting this basic concept of statistics, we've been talking about numerical summaries of data obtained by measurement and computation. We've, in previous lectures, talked about univariate statistics, which look at one variable at a time, bivariate statistics, which look at two variables at a time, and now we're going to move on to multivariate statistics, which look at three or more variables at a time. In this case, we're going to focus on three. In doing so, we're going to recap a bit about the basics and logic of bivariate statistics so we can understand what it is that multivariate statistics are able to tell us and inform us about that bivariate statistics cannot. So as I said, multivariate statistics are going to examine the relationships among three or more variables. As we can with bivariate statistics, we can look at both relationships and differences. So when we're thinking about relationships, are two variables related? This is typically for survey data where we have an independent variable measured at the continuous level and a dependent variable measured at the continuous level. And we can also look at whether groups differ on some DV, in this case, often with experimental data, where we have a categorical independent variable, such as a treatment versus a control group, and a continuous dependent variable. So just like with bivariate statistics, multivariate statistics can be used both with relationships and for differences, and we're going to have a slightly different analysis for both of those situations. Let's start with testing for relationships. Let's first think about the limitations of the bivariate approaches that we talked about last time. So our Pearson's correlation, our Pearson's R, was the bivariate statistic we learned for looking at a relationship between an independent variable and a dependent variable. The main limitation being that it can only account for two variables at a time. But as we've been talking about throughout the semester, particularly early in the semester, is that we may want to account for confounding variables, such as alternative explanations, common causes, in the analysis that we're conducting. We may want to try and statistically account for some of these third variables that might be biasing our estimates of the relationship between our independent variable and our dependent variable. In order to do that, we need an analysis that can account for more than just two variables at a time. And so now we're going to talk about an analysis that can handle as many variables as you can think of, but we'll focus on just three for the moment. And this analysis, this multivariate analysis that will allow us to test for relationships while accounting for three or more variables at a time, is called multiple regression. And what this does is it's going to look at the relationship between the IV and the DV while also controlling for confounding variables. So it's going to tell us what does this relationship look like while we're controlling for these potential confounding variables. Rather than R, as Pearson's R, as we got in the bivariate analysis, we're instead going to get this value called beta, pronounced a beta coefficient, and it's symbolized with the Greek letter beta. So you can see it here, it's sort of like a squiggly B. And when you run the analysis, it's going to be interpreted the same exact way as Pearson's R. So they make it pretty easy for us here that the beta coefficient and Pearson's R are both going to range from -1 to 1. And that number is going to tell us about the strength and direction of the relationship between two variables. What the multivariate analysis, though, will tell us is, does that relationship between the IV and the DV change after we've controlled for confounding variables? So does the beta coefficient look similar to Pearson's R, or does it look much, much different? Is it sort of telling a different story than we had when we were looking at just that bivariate relationship? We've looked at these images already, but just as a kind of visual representation of what we mean when we're looking at these associations or correlations between variables. These are the images we looked at when we introduced Pearson's R for bivariate correlations. Again, the beta coefficient you think about in the exact same way. So these pictures are still relevant here. Is that the direction basically of the slope between of the line on our plot, looking at these x and y values of our independent variable plotted with our dependent variable. The direction of that line, the slope, is going to tell us, is it a positive or negative relationship? Or is it relatively flat, in which case we're not really seeing much of a relationship? And the kind of steepness of that slope is not so important. I don't really want you to think about the steepness very much when we're thinking about what do these relationships look like. But when we have really strong correlations, the clustering of data points tends to be really, really tightly clustered around that line, the depiction of what the correlation looks like. Whereas weak or almost no correlations are going to show a lot less clustering. We're going to see a lot more dispersion of what those data points look like around that correlation line. So again, when we're looking at these depictions, we're just looking at the way the line is facing. Is it pointed upward or is it pointed downward? And then how tightly clustered are these data points around that line? Are they really tightly clustered, indicating that line sort of explains many variables in the data set? Or are they kind of all dispersed all around and not really well explained or well accounted for by that line? If you need a refresher on that, check out the lecture on bivariate statistics. We also have a really cool online, online tool that you can use to actually visualize what different correlations look like and how the line moves around and how the data points move around with different types of correlations. So check that out if you need a refresher. But the key point for us being here that these same concepts apply for interpreting the beta coefficient. So imagine the scenario. Imagine we conduct a survey where we're measuring social media use, attention problems, and stress. And so I'll just quickly put up some descriptions of some measures with some descriptive statistics to say, look, we did a study. We measured social media use by asking participants to estimate how many minutes they used TikTok, Instagram, and YouTube yesterday. We summed across all 3 platforms. We also measured attention problems by asking participants to rate their agreement with 4 items about whether they had difficulty concentrating yesterday. We averaged across all 4 items. And finally, we measured psychological stress by asking participants to rate their agreement with 3 items about how stressed they felt yesterday. We averaged across all 3 items. And again, reporting some descriptive information, the mean, standard deviation for each of these continuously measured variables in this example study. Don't have to worry about what these numbers actually are. They're all made up. But just imagine we have now conducted this study, and we now want to look at what the relationship is between social media use and attention problems, both the bivariate relationship and then also the multivariate relationship when we account for psychological stress. So let's imagine I have conducted this study 3 different times. I've measured social media use, attention problems, and psychological stress 3 different times with 3 different samples, maybe a sample of undergraduates, a sample of adults, and a sample of teenagers. And the first thing I do is run a correlation analysis. So I conduct my Pearson's R correlation, and I'm looking at what that relationship is between social media use and attention problems. And I find in study 1, I get an R of 0.33. I find in study 2, in my second sample, an R of negative 0.65. And I see an R of 0.07 in my third sample in my third study. So as a researcher, if these were the results I got across 3 different studies, I might be a little frustrated because these would be pointing to 3 very different answers to my question of whether or not there's a relationship between social media use and attention problems. In one case, I'm getting a positive value. In one case, I'm getting a negative value. And in one case, I'm getting a value that's basically really close to 0. And so I might say, well, one says it's positive, one says it's negative, one says it's not there. But then you might say, well, maybe there's a third variable, a confounder variable that is interfering with these relationships in some way that's leading me to think that there's 3 very different conclusions across these studies that actually, if I account for that confounder variable, the story might look a little different. So I might want to control for this third variable of stress to kind of partial that out and say, what does the relationship look like once I have accounted for stress? That's the basic idea of what's happening when we conduct a regression analysis. And why this matters is that I could think, well, maybe stress was wildly varying across these 3 samples I collected. Maybe I got a really stressed out sample of teenagers, a really relaxed sample of undergraduates, and maybe a kind of neutral sample of adults. And so if I had 3 samples that really varied on this third variable, it could be meaningfully impacting my estimates about what the relationships are between my focal independent and focal dependent variable, between social media use and attention problems. So let's imagine this hypothetical scenario where in these same 3 studies, I then conduct a multivariate analysis, a regression analysis that accounts for psychological stress. And I might see something like this. Again, this is completely hypothetical, but I now see in study 1, I get a beta coefficient of negative 0.22. In study 2, I get a beta coefficient of negative 0.19. And study 3, I get a beta coefficient of negative 0.30. Now what I'm seeing is a pretty consistent story across these 3 studies, that in all cases, I'm seeing a negative relationship between social media use and attention problems. Now, again, a hypothetical scenario, but this is something that could happen. And what I want you to really understand about this relationship between this relationship between bivariate analyses and multivariate analyses. That when we conduct bivariate analyses, we are not accounting for other potential variables that might be biasing or influencing that relationship between the IV and the DV. Once I account for those variables, it might change the kind of conclusions of what I see between those variables. And in most cases, you want to probably trust the multivariate analysis more so than the bivariate analysis. And you can imagine other things that might happen. So in this case, I'm seeing sort of a consistent story. It might be that once I control for a variable, I get a very inconsistent story of what once was a consistent story, or that before I controlled for that variable, I was thinking there is a relationship between these variables. Once I've controlled for this confounder, it doesn't look like there is any relationship between these variables. And so the main point being that the multivariate analysis, once we've controlled for those confounders, might be leading us to slightly different conclusions. And so it's good to conduct these types of analyses in sequence to see if we're getting the same pattern of results in both cases. We'll pivot now to looking at testing for differences. So if you'll recall from our previous lecture about bivariate analyses, when we were looking for the differences between variables, we were using what was called a t-statistic. The main limitation here being that the t-statistic can only look at 2 groups at a time. So 2 variables with 2 groups. I'm looking at a categorical independent variable, a continuous dependent variable, and I can only compare 2 groups at a time. But in practice, we may often have more than 2 groups that we're interested in comparing. And also, we might want to, again, account for confounding variables, common causes, alternative explanations that we think might be relevant for the analysis that we're doing. So we want to look at an analysis that's going to enable us to account for 2 or more groups at a time and also include these third variables, these confounder variables in the analysis. The analysis that's going to test for differences and allow us to address the limitations of the t-test is what's called an analysis of covariance, or ANCOVA for short. This analysis is going to compare 2 or more groups at a time while also controlling for confounding variables. Now, unlike the t-test, which basically you look for mean differences and then you make conclusions about those mean differences, there's going to be 2 steps that happen when I run an ANCOVA. The first step is that I'm going to get what's called an omnibus F statistic. This statistic is going to tell me, do any groups differ in the sample I've collected? So if I have 3, 4, 5 groups, this first number is going to tell me, hey, does it look like any of these groups differ from one another? A score close to 0 is going to mean that, no, all the group means are pretty much equal. A score greater than 0 is going to mean, groups differ to some degree. This is very similar to this t-statistic we talked about in our bivariate lecture. Just 0 meaning there's not really any differences, numbers bigger than 0 meaning there seems to be some kind of difference. With the t-test, we're just worried about 2 groups. With the ANCOVA, we're worried about multiple groups. So the F statistic just tells us something slightly different, which are the means generally equal, or do some of the means within this multiple group situation seem to differ? And then after that, I'll have some post hoc comparisons where I'm actually comparing each of these groups in my sample to one another. So if I have 3 groups, I'll compare group A to group B, group A to group C, and group B to group C. It's essentially running a bunch of t-tests that compare each of these 2 groups within this kind of larger sample of groups. So that's a lot of hand-wavy, kind of vague description. Let's try to make it a little more practical with some visual examples. This image provides a visual representation of what we're typically looking at when we think about an ANCOVA analysis. So rather than just having two distributions that we're comparing with each other, as we did last time when we compared men and women on different heights, here I might have three different groups, and I want to compare the means of those three different groups. This is going to be really common when we have an experimental design where we've randomly assigned people to different kinds of interventions, different kinds of treatments, and different kinds of controls. And I want to compare each of those groups to each other. But the logic is the same. I'm going to have different mean values for each of those different groups, and I want to statistically compare those mean values while accounting for the amount of kind of dispersion and variability within each of those groups. And so that ANCOVA test is going to allow us to compare those multiple groups simultaneously. And if I want to, it's also going to allow me to control for potential confounder variables, for potential third variables that I would want to account for in my analysis. So imagine we have conducted an experiment where we've invited students into the lab, and we've looked at this example before, where we're having 30 of them scrolling TikTok for 10 minutes, we're having 30 scrolling Instagram for 10 minutes, and we're having 30 sitting quietly for 10 minutes. And after they do this, I measure attention problems by assessing how many minutes they spend on a difficult set of math problems. On average, they're spending in this sample about 5.5 minutes. And the question for me is, do I see differences between these groups and how long they're spending on this difficult task? In essence, are they showing more or less attention problems based on the activity that they've participated in prior? And the ANCOVA is what's going to allow me to compare these three groups simultaneously. Let's take a look at what some hypothetical results would look like for this particular study. Imagine my TikTok group spends about 3 minutes on these difficult problems, my Instagram group spends about 2 minutes on these difficult problems, and my control group spends about 7.5 minutes on these difficult problems. I can look at those means and say, pretty handily, pretty easily, that those who scrolled TikTok or Instagram were spending much less time on these difficult problems than those in the control group. If I want to statistically compare them, the ANCOVA test is what's going to allow me to do that. And because I have 3 or more groups, I need to use that ANCOVA rather than the t-test. And it's going to unfold, as I mentioned, in 2 steps. We're going to first get that omnibus F statistic, which in essence means F statistics close to 0 means not much difference between these means. F statistics greater than 0 means there's some degree of difference between these means. And so that F statistic is first going to say, do we see much variation here? A score of 3.24, I'm going to say, okay, it's not 0, it's bigger than 0. We're seeing some degree of variation in these means. And I'm going to then have to follow that up with some post hoc comparisons to say, where do the mean differences actually emerge? Where do I see the biggest differences or the smallest differences? Basically a series of 3 t-tests that I'm going to conduct here to say, okay, what is the comparison between TikTok and Instagram? What is the comparison between TikTok and control? And what is the comparison between Instagram and control? So in this case, we can see the difference between TikTok and Instagram is much smaller than the difference between our control group and those control group in TikTok and our control group in Instagram. We see a difference of about 0.9 between the 2 social media groups, and then a difference of 4 and 5 for those 2 relative to the control groups, the social media versus control. So this analysis is going to, again, unfold in 2 steps, tell me are there any variation in the means worth looking at, and then if there is, it's going to tell us which means in particular seem to be different from which others. Where do we see big mean differences? Where do we see smaller mean differences? And just to preview, we need some additional statistical information to really make meaning of these. We'll worry about that next week when we talk about statistical significance. For now, just understanding the logic of what we're doing here. Comparing 3 groups, the means of each of these groups, which means differ from which other means, and by how much. Now, laying out this same exact example, we might want to do something even just a bit more complicated, which is I want to compare these 3 groups on attention problems, while also potentially measuring a confounder variable. So measure a variable like psychological stress. So I might say I want to account for how stressed people were when they arrived in the study and say, what is the effect of my experimental intervention over and above this variable of psychological stress. We'll delve into this more in class because it's a bit more complicated, but the logic is the same as we were looking at with that correlation test versus regression, that essentially I could run my analysis and see, does my result change once I have accounted for this potential confounder variable? Do I still see mean differences that are meaningful when I have accounted for this potential confounder variable? So again, the benefit of being able to run these more complex multivariate analyses is that they will allow us to bring in these potential confounders and see, do my results seem to change when I look at this confounder? If so, what does that change look like? And if not, I'm getting pretty consistent results across different kinds of analyses. And just to recap, main learning goals for this lecture is to understand the key types of multivariate statistics. In this case, we're looking at multiple regression and ANCOVA, and this is opposed to the bivariate versions of these analyses, which were correlations and t-tests. And then we're also looking at how to understand these multivariate statistics. The great thing is that they're in large part very similar to both the correlation and the t-test. We're looking at scores ranging from -1 to 1 for the coefficient, the beta coefficient, interpreted the same as that Pearson's correlation. And then for the t-test versus ANCOVA, we're looking at mean differences and how large or small are those mean differences.